Altogether 41 for free molecule. There are 32 for crystal, for solid, if you like, for solid. So I wrote down 32 for solid, exclusive, not exclusively for solid, but solid, and then 9 exclusively for free molecule. And this 32, of course, can be applied to free molecule as well. So a group then is defined. All this notation in group symmetry are related to, of course, group theory. And so when they say group theory, the word group means a lot of things to mathematicians. Group means that you can do operation within that group to generate from one another. So in mathematics, a group has a well-defined meaning. And the chemists follow this concept and connect this sort of group to object, to crystal and so forth, and try to use that as a means to describe our material. Okay? So that's basically what. So from here, a group can be defined as a set of elements. All these things are defined a little bit more in an abstract way because the mathematicians are defining it like that. And each of these elements, you can think of this element or as the operation, can represent a symmetry operation. So like refraction or rotation, inversion, things like that. Okay, and each of these elements, of course, in mathematics, follow some relationship, mathematical relationship, and such as product rule and square and reciprocal. How do you multiply? How do you add and how do you commute and things like that. Okay, so those are all well-defined mathematical rules, which I really don't want to get into. I don't want to teach you a course in group theory because there are other courses that are available to do that, and hopefully you have seen some of this and coming back to you. If not, again, don't worry because you can go to any inorganic chemistry book and read about it. There's probably a chapter on this. And there tends to be, depending on which book you read, some of these are quite mathematical. They explain to you, okay, you take element 1, multiplied by element 2, you get element 3, and this is one of these associative multiplication rule. And if these things are connected to each other, if you can make this sort of connection, then these 3 elements, for example, belong to the group. Okay, so that's the basic idea of this set of mathematical relationship in there. So you can get more precise description if you forgot what groups are in this. But the main thing that I like you to remember, at least qualitatively, is the nature of the point group. Nature of the point group, really, the key thing is this statement here, which leaves at least one point of the object unchanged. Okay, so a point group will contain symmetry element and operation, such as a single atom in a molecule, for example, which will leave that one point, at least one point of that object unchanged. So that's why it's called point group, not space, as opposed to space group. Okay, so we will see later what space group means. So altogether then, there are 32 three-dimensional point groups that can be used for crystal, right, which is the bulk that we're talking about, and as well as free molecule. And then there are 9 exclusively that can only be used for free molecule, cannot be used for crystal. This is why I say 32 plus 9, 32 for crystal, and 41 altogether for free molecule that can be described in this way. And here they are, all 41 of these point group. You don't need to memorize these things. Just for your future interest, in case you come across these are some example, like molecular example, like latest acid or NF3 or this organic material, BF3, things like this. And these are the group. Okay. designation here. I'll talk a little bit more about these. These are known as class or type. Class or system, there are 7 class or 7 type or 7 system, depending on which book. Again, the jargon is not very universal, but these are 41 of them. They have different designation. They are one definition, which is well familiar with the Camus, T for tetrahedron and O for octahedron, this sort of thing. This notation, the Hermann notation, is more of a crystallographer, X-ray crystallographer notation. So they are very complex in many ways. Most people are familiar with this, but sometimes when you read journals, you may come across these Hermann notation, which are just basically point group notation. So I want you to be aware of these connection between these, and you really don't need to memorize these because it just for your interest as a way to explain. For example, a C1 group is really just have the identity. C1, of course, has essentially no symmetry because you have to rotate to get back to the same point 360 degrees, right? That's C1. And so it's essentially just have one symmetry operation, just to identify that. And then, of course, this one, this point group T has these several operation or element within that group to make up this group in there. Okay, and so these are the crystal structure that you may see, and you can see a lot of them are salts, right? Some are metal. We'll get to it when we talk a little bit more about structure. Okay, so it's quite interesting. It is the 41, 32 apply to crystal. Now we have in this table we have indicate 2 type of notation. Usually we use this one. Crystallography use this one, and you'll also notice that they are separated into 7 classes. Sometimes it's called classes. Okay, so this 41 or 32 rather, 32 crystal point group applied to crystal can be separated into classes, and classes really is additional layer. You can think of classes as an additional layer of mathematics that connect this group. So, for example, these 2 can be interchanged by a transformation mathematic like this, right? So you can, if this is A belong to C1 and B belong to Ci group, then you can transform them using some sort of transformation in this way. Okay, so A X inverse, this is a transformation matrix, and then operate on B, and then the normal of X. Okay. Again, if you don't know, sometimes people may not be aware of how to write these symmetry group in matrix form. Don't worry about it, because this is if you don't know what the word conjugate is, again, don't worry too much about it, because the physicists of the group may know what conjugate means. Right? And these are typical, just think of this as typical mathematic transformation that you do. You put in B and then you do something to it, X multiplied by X matrix, and then the inverse of H in this way, and then you get back A, right? So this is kind of a transformation matrix. And if you can do this, then A and B are called conjugate. So you have A and B are conjugate, and then they belong to this class. Right? So you can take this 32 group element that you have, and if you can figure out some X transformation matrix that generate them each other, and then you find out they sense to separate, because there are other, you cannot cross these 2, because you can never find an X matrix that can transform into, say, C2 2X, for example. If you start